So moving on, Khan Academy. So again, you don't necessarily have to do something on this page here. I'm going to look up your grade, but if you want to submit that you did it all just to kick me in the butt to go look it up, go for it. So we're going to do this things you find on a paper circle. Now I have this printable version here, which I showed a moment ago on the camera. I'll show it again in a minute. So if you wanted to print this to write on, you could, but you don't need to. All I need from you on this is in the submission box for this, anytime I ask a question like 1, 2, 3, I need an answer to that question. Whether that answer is a sentence or a number with a sentence, I need something. So, and then otherwise, if it doesn't have a number, that's something you need to do with your circle. So I'm going to walk through all of this with you. I'm going to talk about the answers to these, but I'm not going to write them down. So it would be good to have this on a screen nearby, or maybe you have the paper version. So you want to take some notes as we go through this. I'm going to go over some of these, let's see, at the end here, but I'm going to leave some of them for homework for you to play with. Okay. So anything with a number requires an answer, and those are the things that need submitted. Other things here are just instructions on what we're going to do with our circle. So if you don't already have a paper circle, please, and you're in the future, please pause the video, find yourself a piece of paper, cut a circle out of it. I did so by tracing a bowl. I'm going to switch to my camera. All right. So here is my circle, and you can see I've already folded it. I'll take it. Come back to that one. This one a little wrinkled. The first thing I want to do is just make a note. A circle is a plane figure. Plane figure is a figure that lives in a flat plane. So any figure you can draw on a piece of paper is a plane figure. This plane figure is simple. It's got an edge that comes around it. That edge does not intersect itself, and it's closed, or it's not open. So that edge is closed around the outside. The circle technically is the edge. Its circumference is the circle. The inside is its area, and sometimes the inside of a circle is referred to as a disk. So the edge is the circle, the inside is a disk. But usually we kind of don't differentiate with young kids. The circle is this whole thing and its edge. So first thing we're going to do is we're going to fold the circle in half to the best of our ability. And if you cut out a reasonable circle from a reasonably circular object, it should work out pretty nice. So get that top edge to line up, check around the sides. If you think you got it good, crease across. And so here is my semicircle. The line at the bottom of the semicircle goes through the center of the circle. A line that goes through the center of a circle is the diameter. And if I move too fast on something and you have a question, please let me know in the chat or through voice. If I open it up, I can clearly see the shadow that diameter forms for me through the center there. Semicircle above, semicircle below. A semicircle has half the area of the original circle. What we're going to do is we're going to make another fold. So any direction you want, it could be perpendicular to that one or at some angle, but we need to fold the circle in half again. Again, do your best to line up that top. Make sure the edges seem good, and then make your crease. And the better we fold here, the better the whole thing will work out. So again, if I open this up, I now have two diameters. And a diameter is a line that runs through the circle and passes through the center. Since both of these pass through the center, we can see the center where they meet. So what we're going to do is we're going to take a pen or a pencil, and we're going to carefully make a small point at that center there. So that's too small. A little tiny bit bigger. See that there on the camera? Yeah. So my two diameters meet right there in the center to the best of my ability. I believe that's the center. It's a tiny bit off, but hopefully it's close enough. for fun, what we're going to do is make a third fold in a different direction than the other two and see what happens. So again, we line that up at the top, make sure it's not too far, either direction, above or below, and then make your crease. And we want to be neat. And depending on the age group, so this is an activity that's really designed for kids at different ages. And if they're too young, like first graders, kindergartners are going to struggle with these folds. Second graders, half of them will do a good job. Third graders, it gets better. All right, so what it looks like is that other fold does pass through my center there. So I think I put my center in a pretty good spot there, and my circle's pretty decent. So I have 3 lines that pass through the center. Each line is a diameter. If I go from the center to the edge, that would be a radius of the circle. And then following around the whole edge is the perimeter or circumference of the circle. So for general figures, we say the distance around is the perimeter. The circle gets a special name. It's called the circumference. Okay. Next thing we're going to do. We are going to fold an edge of the circle so that it perfectly passes through the center. So fold that edge, get it down right through the middle of your center, hold it, and then crease it across. And so I now have a fraction of the whole circle. We got this smaller flap here and the bigger flap here, right? Small flap, flap. Open it up, flatten it out a little bit. So this line passes through the circle, but it does not pass through the center. So you have a line that goes through the circle, but not the center. It's called a chord. So that line is a chord. These other lines are actually chords too, but since they go through the center, a better name for them is a diameter. That one definitely is not a diameter. Now, we're going to do that again. We're going to take an edge, different from that part of the edge, and fold it to the center. But what I want to have happen is the new chord that gets made, I want to meet perfectly where that chord meets the edge, right there. The easiest way to do that is to fold this first one back the way it was. I can still see my center right there, just barely, right, hiding under there. And then here, I'm going to get that fold to start at the edge, and then I'm going to kind of gently twist so that I have a nice point here, and this edge of the circle touches the center. And I don't want the center to go away, and I don't want to overfold up there. So you're just going to kind of gently tease the paper into the right position. Once you think you have it in the right spot here and here, then gently try to make your crease. And my point's not quite as sharp as I made it earlier, but it's good enough there. And I can just barely see my center there. Notice that little bit of dark shadow there. I can still just barely see my center. And I've made an ice cream cone. Question, can we do that one more time? Can we fold the remaining edge of the circle to the center so that we touch this edge of the chord there? And what would happen on the other edge? So give it a try. So just like before, I'm going to start the fold up there without overfolding, and then gently twist till I get the edge at the center. Double check I'm in the right spot up there. And then I'm kind of wondering what's going to happen on the other side. And wow, it looks like I have a perfect point here and there, and all 3 meet in the center. I have a tiny gap on mine right there where the center is. So all 3 edges of the circle that we folded in should touch the center. And hopefully if our folds went well, we have a sharp point on each part. And we've made a special triangle here. All right, any problems? Is that going okay to this point? Okay, I got a thumbs up. Cool. So I'm just going to open this up for fun. So I can see here, when I open it up, I have a triangle, and the points of the triangle, they're technically called vertices, touch the edge of the circle. So if you have a figure like a triangle, and its points, its vertices, vertex, each vertex is a point, each point is a vertex. If they touch the edge of another object perfectly, then we say the triangle is inscribed in the circle. So to inscribe means to put one figure in the other so that vertices touch edges. So this triangle is inscribed in the circle. Now, I created this triangle. Each edge was created the same way, by folding the edge of the circle to the circle's center, by folding the edge of the circle to the circle's center. And each edge of the triangle here meets the adjacent edge. Adjacent means next to. So this edge of the triangle is adjacent to that edge. This edge on the right is adjacent to this bottom one. So any two edges that meet in a point are called adjacent edges. And it turns out on a triangle, every pair of edges are adjacent. All right. So other things, since this triangle was created so that each edge was formed the exact same way, then each of the edges and angles between those edges are the same. So I have 1, 2, 3 angles that are the same, congruent, and I have 1, 2, 3 edges that are the same or congruent. So if you have a figure, a plane figure that has the same length edges all the way around and the same angles all the way around, it's called regular. A regular triangle is also called an equilateral triangle. So at this point we have an equilateral triangle. Sometimes called a regular triangle. It's also an equiangular triangle. To be regular, you have to be equilateral and equiangular. We'll talk more about that in the next section. Okay, next step. What we want to do is take two vertices of the triangle, and we want to bring them to touch. I don't want to fold the triangle completely in half, but I do want to know where the center of this side is. So what I'm going to do is I'm going to get those vertices to touch, and then I'm just going to crease that bottom so I know where the center of that edge is, and I'm going to make a mark there. So what I need to know is the center of one edge of my triangle. Now, compared to this edge right there, this vertex is adjacent because it's at the end. This vertex is adjacent, but way down here, this vertex doesn't have anything to do with that edge. It would be opposite that edge. So I want to take this opposite vertex and I want to fold it down to that midpoint there. So it just gets to the edge of the paper right at that midpoint. And then I want to crease the top there. I just realized I had a piece of paper sitting on my mic, and I apologize if you couldn't hear me very well. I hope it's better right now. Okay, so again, I had to mark the center by making the vertices meet, crease to get that middle, and then mark it. Then from that edge, I took the opposite vertex, touched that very edge of the center of that edge, and I made a crease. So I've made a new shape here. This shape right here, I'm going to flip it over this way, has 1, 2, 3, 4 sides. It's no longer a triangle. So what's a good name for this? Well, there's a lot of different names for it. It has 4 sides, and a 4-sided plane figure is called a quadrilateral. So this is a quadrilateral. Now, this quadrilateral has a pair of parallel sides due to the way I created it. So this bottom edge, that long bottom edge, and this shorter top edge, these two are parallel. If you have a 4-sided figure with a pair of parallel sides, it's called a trapezoid. Now this trapezoid has another property because this angle down here matches that angle due to the original triangle. And because these two sides are parallel, this angle and that angle are also going to be equal. So this right here is called an isosceles trapezoid. Kind of like isosceles triangle. Isosceles triangle is a triangle where two sides have the same measure. And here I have these two sides with the same measure. So it's a trapezoid because it has four sides and a pair of parallel edges. And it's isosceles because the other two edges are congruent. So this best name for this sucker right here is an isosceles trapezoid. Now, a couple things to consider here. I have this flap that I folded down here. I'm wondering, that is a new triangle right there. That new triangle is part of the original big triangle. What part of the big triangle is this new smaller triangle? So this new smaller triangle is what part of the original triangle? Any thoughts on that? How many of these fit in here? And when I fold it down, I kind of get a clue on that right there. How many triangles do we see here? 1, 2, 3, but then I fold it open and there's a fourth. So here I have 1, 2, 3, 4 congruent triangles that make the big one. So this smaller one here must be 1/4 of the original triangle. The trapezoid is what part of the original triangle? Trapezoid, this is the trapezoid here too, is what part of the original triangle? Let's see. The trapezoid has 1, 2, 3 triangles in it. The original triangle has 1, 2, 3, 4. So the trapezoid must be 3/4 of the original triangle. Okay. So next, what we're going to do here is we're going to make another fold. Now, we talked about acute angles and obtuse angles before. So acute is less than 90, obtuse is greater than 90. So in this trapezoid I have right here, I have this acute angle and that acute angle. This would be an obtuse angle and that would be an obtuse angle. So what I want to do is I want to take one of the acute angles and I want to take that vertex and fold it to an opposite vertex. So let's talk about opposite versus adjacent again. So this vertex right here is adjacent to that vertex right there because they have an edge connecting them. This vertex right here is not adjacent to that vertex right there because there is not an outside edge connecting them. So these two vertices here would be considered opposite vertices, whereas these two are adjacent. So I want to take this acute vertex and fold it so that it perfectly touches, to the best of my folding ability, that opposite vertex. Now the thickness in the paper is going to interfere with us a little bit, so it's not going to be perfect. Get as close as you can and then crease. So basically I'm taking this triangle right here and folding it on top of this middle triangle to get a new shape. So here's my new shape. Again, if you missed something, pause the video, try again, or just ask me if you're live. New shape here. It has 1, 2, 3, 4 sides. It's a quadrilateral. This quadrilateral has a pair of parallel sides here and here, so it's a trapezoid. However, it has another pair of parallel sides, so it's a parallelogram. So this one has a lot of names. I could call it a quadrilateral. I could call it a trapezoid. I could call it a parallelogram. So far, parallelogram is the most descriptive name for this. Parallelogram is a four-sided figure with two pairs of parallel lines. However, since this parallelogram is made up of these equilateral triangles here, that means each edge of this parallelogram is the same. So I could say this is an equilateral parallelogram. Better name for an equilateral parallelogram is a rhombus. So lots of names we can give these figures based on properties of geometric figures. Best name for this one right here is a rhombus. A rhombus is a four-sided figure with equal edges. So this has 1, 2, 3, 4 equal edges. It's a rhombus. Rhombus is a kind of parallelogram. Kind of like a square is a kind of rectangle. Question. This rhombus right here is what part of the trapezoid here? Right? The rhombus is smaller than the trapezoid. So the rhombus is what part of the trapezoid? Let's see, the rhombus has 1, 2 of these equilateral triangles in it. The trapezoid has 3, so the rhombus must be 2/3 of the trapezoid. I could ask another question. The rhombus here is what part of the original big triangle here? Well, again, the rhombus has 1, 2 of these equilateral triangles in it. The original triangle has 1, 2, 3, 4. So I could say the rhombus is 2/4 of the equilateral, the large equilateral triangle. And we have a couple triangles floating around. We have this large one here, and we have this medium one here, or this smaller one here. I say medium now, I let the cat out of the bag. We're going to have a smaller triangle in a minute. Okay. Moving on. Back to the rhombus here. We are going to take this acute vertex. This would be an obtuse vertex. We're going to take that acute vertex and fold it to the other acute, opposite vertex. So this vertex on the left, fold it over so it gets as close as I can get there. The thickness of the paper, if I had thinner paper like for, what's that Japanese folding stuff called origami. If I had origami paper, this would be easier. I don't have any with me. So this is my best version of it. So I now have it down to that smaller triangle that we've been using as like our measuring stick. So that small triangle right here is 1/2 of the rhombus. This triangle right here is 1/3 of the trapezoid. And this small triangle right here is 1/4. Kind of see it better on this side here, is 1/4 of the original large triangle. Now I can also go the other way with these kinds of things. I can say the trapezoid is how many times larger than the triangle. So that would be 3 to 1, or just 3 times larger. This one's a little harder. The trapezoid is how many times larger than the rhombus? Now I know the rhombus is 2/3 of the trapezoid, so I've asked that the other way. The trapezoid must be 3/2 of the rhombus. So any question we ask in one direction, we can ask it the other direction. If it was a proper fraction in one direction, it's going to be an improper fraction in the other. So the rhombus is 2/3 the size of the trapezoid. Going the other way, the trapezoid is 3/2, 3/2, 1.5 times the size of the rhombus. So again, we can answer those questions in either direction. So a little review of fraction comparisons there. All right, so I'm going to do something new. instead of folding these all the way down, what I'm going to do is I'm going to push each of these triangles up so I make a three-dimensional shape so that the points of the original triangle all touch each other up above here. So I'm just going to adjust mine a little bit. So I have this three-dimensional shape here. And so I'd like you to look at it for a minute, and I would like you to count how many flat sides does this thing have? So looking at it this way, I count 1, 2, 3 coming around the top, and then if I flip it over, there's that one on the bottom. So I count 4. This has 4 flat sides. Those flat sides are technically called faces, and we call them faces instead of sides because often with a triangle, some people will call the edge of a triangle a side. So what's a side really? So side is a non-technical term in geometry. Technical terms are these lines here are edges, and these flat surfaces are called faces. So I have faces, edges, and the points where things meet are vertices. Singular is vertex. So this is a three-dimensional object. It is not a plane figure, right? It's not flat. A four-sided shape like this one right here is called a tetra, is another word for four. Hedron refers to these flat faces here. So tetrahedron. This has 4 flat faces, three-dimensional tetrahedron. The tetrahedron has an area. I can paint it. How does the area outside this tetrahedron relate to the original triangle? Well, wait, I think the original triangle is the outside of the tetrahedron. So the tetrahedron has the same surface area as this side of the triangle. So the area of this triangle right here is the surface area of the tetrahedron. All right, new project. So flatten your shape out, kind of smooth out those folds a little bit because we're going to make a new set of folds here. Fold it over so you can see the flaps of your circle again. And hopefully you can identify the center of the triangle, which is also the center of the original circle, right? There's my center. So again, if you're kind of caught in the action of this folding and thinking about what everything means, the whole point of this exercise, the main thing is just by playing around with a piece of paper to get all these geometric ideas out there, right? Talk about these ideas. What's an edge? What's a face? What's a vertex? What's opposite? What's adjacent? How do these compare? Okay, so here's what I'm going to do next. I'm going to pick one of my vertices. So I'm going to pick this one right here. And what I want to do is I want that vertex to perfectly touch the center of my circle. So fold it down so that it goes to the center. I'm going to hold that there and come back and crease. Okay. Now, if I did a good job of getting that to the center and I made my crease, what should happen is this new edge here should be parallel to that edge at the bottom. We don't have a good way to measure its parallelness. We're just going to go for it and say, yeah, I did a good job folding. Good job, thanks. Good job, Brianna, good job. Emily, good job, Gary. Now, I have a new shape here. What is my new shape? Flatten it out a little bit. Okay, let's see, it has 1, 2, 3, 4 sides. So it is a quadrilateral. Technically, they're edges, right? I misspoke there. I'll do that a lot. It's okay. Okay, so quadrilateral. But I claim that if my folds were good, this long edge there and this short edge there, they should be parallel. If I have a pair of parallel sides, then this should be a trapezoid, right? Now, my original triangle was equilateral, equiangular. So those two angles were the same. If this line rarely is parallel to that line, then these two angles up here should be the same. And these two lines over here, these two edges should be equal, congruent. So if I have a trapezoid that has a pair of congruent opposite edges like that, then this would be an isosceles trapezoid, kind of like an isosceles triangle. Isosceles triangle is a triangle that has a pair of equal congruent edges. Now this one actually has a third one, so it's equilateral, but it's kind of also isosceles. The best name for this sucker is an isosceles trapezoid. Notice it's bigger than my first isosceles trapezoid. That's my first isosceles trapezoid. This is the second. And like the most challenging question, I think, for this problem is this smaller isosceles trapezoid is what fraction of this bigger one? That's a tricky question. I'm going to leave that out in the open for now. I'll answer that next week. But if you want to try and answer it before then, it's a good thing. Okay, we're going to do that again. So I'm on the inside where I have that flap folded down, where I have my edges of my circle. And I'm just going to pick a different edge here. And I'm going to fold that into the center, just like before. Hold it there, and then crease neatly. So usually I try to move back from where a point is to the crease. And if I did a good job there and open it up and leave that one, I have that same isosceles trapezoid, just from a different side. So here it is from there, or here it is from there. Now, with two of them there, this is a whole new shape. What is this shape right here? Well, I might want to call it a diamond. It looks kind of diamondish, but let's see, how many sides does it have? If I start down here, I have 1, 2, 3, 4, 5 edges. So 5 edges would be called a pentagon. This is a pentagon. Diamond isn't really a plane figure, although we'll call lots of plane figures diamonds, but that's not a technical geometry term. So this is a pentagon. It's got some nice symmetry to it, but it's a pentagon. All right, another time. We have this last acute vertex here. Guess what we're going to do with it? We're going to take it and bring it down to the center. Hold it, try to gently get that crease going, and then more forcibly, and we got this new shape here. So this new shape I've got here, starting down here, has 1, 2, 3, 4, 5, back to here, 6 edges. So it's no longer a pentagon, right? That was the pentagon. This is now a hexagon. Hex is another word for 6. Okay, what else do I know about this hexagon? Well, interestingly, once I fold these acute vertices down to the center, not only do I make this triangle here, which happens to be just like that folded one there and that folded one there, but the other 3 triangles in between turn out, because this was equilateral and equiangular, this new thing is also equilateral and equiangular. So the best name for this sucker right here is a regular hexagon. Now, let's notice something about this hexagon. This particular hexagon is made up of 1, 2, 3, 4, 5, 6 triangles that meet in the center. If I think about those 6 triangles and unfold them, I now have a 7th one out there, an 8th one out there, and a 9th one down here. So I have the 6 in the middle, and when they're unfolded, I have 7, 8, 9. So the hexagon is made up of 6 of these little triangles. The original triangle is 9, so the hexagon must be 6/9 of the size of the original triangle. 6/9. That kind of cleans up a little bit, right? So let's think about that. Here you could say I have 2 groups of 3. And then when I open these 3 out, I now have 3 groups of 3 triangles. 2 groups of 3, 3 groups of 3. So that means the hexagon is 2/3 the size of the original triangle. So I could say 6/9. There's nothing wrong with that. The hexagon is definitely 6/9 of the original triangle. But because here I see 1, 2, 3, and another 1, 2, 3, I have 2 groups of 3 triangles there. Opening those up, I have a third group of 3. Getting rid of those extra groups of 3, we have 2 thirds. All right, let's see. This right here is a pentagon, right? The hexagon is what fraction of the pentagon? Okay, let's see. The hexagon has 6 of these triangles. The pentagon has 7. So the hexagon must be 6/7 of the original, sorry, not the original triangle, of the pentagon. The hexagon is 6/7 of that pentagon there. If I compare the hexagon to this version of the isosceles trapezoid, so this is my second isosceles trapezoid, that was the first one. The hexagon has 6 of these triangles. This isosceles trapezoid has, let's see, 6, 7, 8. So it would be, the hexagon is 6/8 the size of this second isosceles trapezoid. That's a mouthful. All right, I'll show you something cool here. We're almost done with this. And then there's a few questions you'll have to come up with on your own, and we'll compare notes later. Now remember, if I didn't make these extra folds here, I've got that tetrahedron, but now that tetrahedron's wanting to have these extra folds on it. Okay, so here's what we're going to do. From the tetrahedron, we're going to let these folds kind of fall down on each other. And what we should find is they should sit on top of each other quite nicely. See that? Is yours doing that? If your folds are good, then those flaps of the tetrahedron should sit on top of each other. Now, to the best of our folding ability and because of the thickness of the paper or the irregularities of our circle, they're not going to be perfect, but these 3 smaller triangular flaps are theoretically the same, exactly the same shape and size. So they could fit nicely on top of each other. And if you find you can tuck one point into the flap of another, and that last one can go underneath the 2 of them, and it will kind of stay almost like that. It's being a little finicky today. Almost. So this is a tetrahedron with the top chopped off. Turns out this smaller top is parallel to the larger bottom. It's kind of cool because of the way we made our folds. When you chop the top off something, there we go. In math, we say it's been truncated. So I could call this a truncated tetrahedron. Now, one thing I'm wondering about the truncated tetrahedron is I think it has less surface area to paint than the original tetrahedron. So I'm wondering, I'm going to answer this question and we'll stop there. The truncated tetrahedron with the flaps down is what fraction of the surface area of the original tetrahedron? And to answer that, I just have to think about what's happening here. Okay, so here's the original tetrahedron, and then these flaps get folded down. And instead of having those 3 flaps to paint, 2 of them are hidden underneath. So I lost 2 of those flaps. If I think back to my hexagon here, right, those flaps came from this hexagon. There were 6 of those triangular pieces. 7, 8, 9 gives me the original triangle. So the original triangle and the tetrahedron have 9 of those little triangles. But when I fold to get the truncated one, I lose 2. So I think then that the truncated tetrahedron has 7 out of the 9 little triangles of the original triangle or the tetrahedron. So I think the truncated tetrahedron is 7/9 the area of the full tetrahedron. So I have 2 goals here. 1, I wanted to play with 3 goals. 1, I wanted to play with a piece of paper and make something cute. 2, I wanted to talk about these geometric concepts like parallel, equiangular, equilateral, acute vertices, and obtuse vertices, and adjacent vertices, and triangles, and quadrilaterals, and pentagons, and hexagons. So there's so much geometry hiding in this little bitty circle here. I thought it was a very exciting activity. All right, so we've answered 95% of the questions on that activity. I'm going to come back to that here. Let's share screen. So this version right here can be printed. It prints okay. I had another copy of it here that is designed to print. This is a video of me from last year kind of going through this and tracing it out on a screen. But hopefully you found answers to each of these questions as we moved through this. And this video is recorded if you want to come back and check it out later. And the only thing I didn't answer all of these last few questions here, but I answered a lot of them. So what's next? Well, next is to check out the Khan Academy homework if you haven't already, and then write up on paper or type into the submission box your answers for this. So again, what should happen is on your version, you should see a start assignment button here that used to say submit. They changed the way that said stuff. And then in text entry, you could just enter your answers for 1, 2, 3, 4, and so on. If you wrote it on a piece of paper, then you could take a picture of it and you could upload that file. Or if you did it in a Google Doc, you could just link the shareable link to your Google Doc. So however you want to turn that in. Questions? Okay, then we are done with this activity.